everyone. So in the last class we discussed Jacobian that relates the joint rates to the end effector rates. We saw how a Jacobian can be calculated for a 2-hour planar arm. We also saw vector matrix approach for calculating Jacobian of a general n degrees of freedom robotic arm. Moving ahead further, today we'll be discussing general Jacobian formulation further, and we'll do Jacobian for a 2-hour manipulator using vector matrix approach. We'll understand what is singularity of a robot, and we'll also do acceleration analysis. So let us move further. Okay, so this was our general Jacobian matrix. So let us just quickly recapitulate what was there. So general Jacobian matrix can be written like this. This consists of a end effector twist that is here, which is nothing but a column matrix of 6 cross 1. So this is the Jacobian matrix and these are the joint rates. Okay. So in general, it can be written as J omega JV, which is nothing but matrix which can be written like this. So this becomes your J omega and this becomes your JV. So it is EI on the top 3 rows and EI cross A1, E, A2, E, A, N, E, likewise it has in this row. So what were all the variables? So EI were the joint axis vector. So this was E2, E1, E3, right? So it was like that. For ith link, it is EI which was oriented like this. So these were all unit vectors that is along the axis of that link. Okay. And then you have EI A1E cross product. Okay. So what is that? 1E is nothing but the vector, the position vector that connects like this. So this is 1 to E. Then you have 2E. Okay. Then you have AI to E. Likewise, it will continue. So you understood what it is, general Jacobian matrix. So let us just use this and see if we can calculate 2-hour planar manipulator Jacobian using general Jacobian matrix. Okay. Thus, so our 2 degree of freedom planar manipulator looks like this. Let us just talk about the variables what are there. So this is A1, that is link length. A2 is the second link length. Theta 1 is the joint variable, that is the joint angular displacement, that is measured like this. Then you have relative angle theta 2, that is again measured about the extension of the first link. Okay, so this is like this. This is all planar. Okay, so simplified expression for Jacobian, because you know it is just a positioning robot, there won't be any angular velocity part of the Jacobian. J omega will be absent. So let us not calculate it also. So it becomes a simplified Jacobian. So it has just E1, A1E, E2, A2E. Those elements are to be found out for this particular robot. So what are E1 and E2? You know, E1 and E2 are directed perpendicular to this plane. Okay. It is perpendicular to the XY plane. So it may be given as 0, 0 and 1. Okay. So it is directed like this. It is perpendicular to the plane of this. So both becomes the same. Okay. One is placed here, other one is placed here. Okay. So that is E1 and E2. So now what is A1E? A1 to the end effector. Where is your end effector? It is here. So let us just connect it. A1E. So this is the vector, which is nothing but A1 vector plus A2 vector. So you already know what they are. So how much is this? This is A1 C1. This is A1 S1. Similarly, what is this? It is A2 C12 and this one is A2 S12. Got it? So if you calculate the x coordinate of the end effector, so that is A1 C1 plus A2 C12. So that is your x coordinate of the end effector. So that is, I am talking about this point which is here. Similarly, this point is A1 S1 plus A2 S12, and because it is a planar manipulator, so you have the point over here, so with coordinate Z as 0. So this becomes your vector A1 E, A1 to E. Okay. Similarly, A2 is nothing but this distance. It is this vector. It goes from here to here. And that is very simple. It is simply A2 cos 12, that is this. And A2 S12, that is this. And you have 0 here. So these are the two variables which are now known. So we now know this. We also know this for both the links. Okay. So I can quickly take the cross product. E2 A2E, E2 A2E. I have started from this end. So I, J, K, you can put it like this. Standard method of taking cross product. So it becomes 0, 0, 1. So this is your E2, it is 0, 0, 1. And A2E, that goes here. Got it? So taking the cross product, you can quickly obtain this. Similarly, you can take cross product of E1 and A1E. Okay. So what is that? If you do it in a similar manner using E1, that is this, and A1E, that is this, you can quickly obtain this. Got it? So now I can put them together in the form of matrix. I have just extracted out the 0th term. So that was K vector, which is absent here. Similarly, K that is absent here. This is 0K. So that I have simply eliminated and I have written JV as this. So this is your Jacobian. So if you write them in column manner, so it is minus A2 S12, it is here. Okay, and A2 C12, it is here. This comes here. This one will go here. So this is your Jacobian. This relates the joint rates theta 1 dot, theta 2 dot to the end effector rates, that is X dot and Y dot. Got it? So this is 2 cross 2 matrix. Very simple. So now let us just compare what we have obtained earlier using simple differentiation way. So we did it simply by differentiating the forward kinematics equation, that is X is equal to this, Y is equal to this, taking derivative, expanding and rearranging in the matrix form, it gave me this. Okay. This you see, it is exactly the same. It is exactly the same. Okay. So this is how you can use a general Jacobian matrix for n degree of freedom serial chain system to calculate the Jacobian for your robotic arm. So if you have all the informations, you can quickly do it. So now let us work out where to extract all those parameters. Basically, EI and AIE. Those were the parameters which was required to do Jacobian. Okay. So let us just find out where are they. So you know these are all z-axes about which your link is rotating. So if we talk about theta 2, it is about this which was measured. So if we just simply can look at the homogeneous transformation matrix, what are informations which are there? So what is this? This is nothing but the frame which is attached to the ith link, at the end of ith link. Okay, if we talk about Ti, so that basically includes all the link transformation matrix A1, A2 and so on so forth till AI. What is this effect? Actually, it is I minus 1 I. So what was this? This was giving me the position of this frame. If you take it till I, it should give you this. So what is that? That is nothing but position vector of this. Okay. That is attached at the end of the link. So this is attached at the end of the ith link. So this is this one. Okay. So it quickly gives me OI plus 1. Got it? Similarly, so you can do it for all. So if it is T1, it gives you the location of this. If it is T2, this one will give you the location of this. If it is for sixth link, let us say this is a 6 degrees of freedom robot. So it will give you the position of, I assume this also includes the tool which is there, all the end effector dimension which is there, because it is permanently mounted without any joint at the end of the last link. So if that is included, so this is your position that will be given by T6. Got it? So 1, 2, 3, 4, 5, 6. At the end of 6th link, you get this position. This you know, this is always equal to 0. It is attached to the base frame of the robot. So you start from 0, go till n for n degrees of freedom robot. So you will quickly get the vectors which are directly connected from here to this, here to this, here to this, like that. Okay, so you will obtain them all. Okay, so this is just giving you these informations. Now let us move ahead. Okay, so what is this? This is E1. E1 can be straight away written as 0, 0, 1. Why? Because that is the first axis which is placed at the base of the robot. So you know displacement axis is along Z axis. So in case of rotary it is the same. In case of prismatic also it is along Z axis. So E1 becomes 0, 0, 1. What is E2? E2 is nothing but that is placed at the end of first link. So you can quickly extract it from here at the end of first transformation matrix. So that is also equivalent to A1. So it is this row of this. Okay, so it is 1, 2, 3 element of the third column. Got it? So that is here. And similarly E3, E4, E5 and E6. E6 you have ended till here because you know this is the one, the second last one. Okay, so that is exactly giving you the location which is here. Okay, so that is your E6. Axis 6 vector is placed at the end of link 5. So that is where you will obtain it. Okay, now you just see if you know all these terms. So this is what is required. So E1 is known. Now you have to calculate A1E, A2E, ANE. So where you can obtain that, you know, this can be obtained directly by T6. That is homogeneous transformation matrix that comes till there A1, A2, AI plus 1 and finally AN. So till you take the product of all of them, so you will reach till this point. So if it is 6 degree of freedom robot, so you have to take product till 6 and at the end of 6, you have this frame. Okay, so that will give you the tip position. So that is T6. So this is your A1E. How you will calculate is 1 to E. So that is nothing but frame 1 to how to calculate A2 to E? Let us see. So if this is your 2 to E, how will you obtain it? So you have to take the difference. So you already know this. Okay, this end effector location is already known from the T6. This column is basically giving you 1 to E. So that you already know. So this you have already obtained, that is PE. That is the end effector location. Now you already know this also. How? That is basically the T1. So if it is T1, so you have reached till here. T1, this. So it is the fourth column, first 3 row elements. So that is your vector, which is this. Got it? So now using this vector triangle, so you know this, you can quickly calculate, that is A2E. So that is PE minus P1. So this is your P1. Got it? P's are all, if it is homogeneous transformation matrix, this is Px, Py and Pz1. So this is the column that I am talking about. This will give you for any transformation matrix. So this will give you the position vector of the corresponding frames which are placed at the end of the link. So this is it. So this is P1. Now let us move ahead and see how you can calculate for let's say if it is A3E, that is from here. So how will you calculate it? So you have to take product of A1, A2. That means you have reached till this point. So this vector is now known. You already know this vector. So using vector triangle, you can calculate this very easily. Okay. So that uses T2, that is A1 into A2. So that is how you can obtain. For any of them, you can obtain. So this is how you will obtain all the vectors. And now you already know A1E, A2E, these vectors are known. This was known previously. So now you have to take cross products. So what are these? Jacobian, if you remember, this first 3, 1 and the next 3, 1. The first 3 were E and next 3 were E cross A1, E, A2E, AIE, like that. So you have simply put those values to this matrix. So these are just element to element transfers using the cross product. So cross product result will go to elements in the row 4, 5, 6. In the row 1, 2, 3, this will go. Got it? And for all the degrees of freedom will come like this. Okay. So this is how it is done. An equivalent function in MATLAB, it is cross product of E6, A6C. It is just a method to take cross product. If you know these two vectors, you can quickly do that. So this is how it is extracted out of your standard kinematic transformation matrices, and you can do Jacobian. Okay. So this is how Jacobian can be obtained using any programming technique. Okay. Now Jacobian inverse. Why is that required? You already have this in hand, twist vector. That is nothing but a vector containing angular velocity and linear velocity over here, that is known as twist, is equal to Jacobian times of joint rates. If it is n degree of freedom, Jacobian is 6 cross n, and this is n cross 1. N degrees of freedom will have n joint variables, and this is always 6 cross 1, because you know at the end you have 6 variables only, 3 for position and 3 for rotation. Okay, so that is there always. So if you have to take Jacobian inverse, that is to obtain joint rates, this is already given. So if you know the end effector rates, can you calculate the joint rates? So this is the way you can do it. Okay. So this is quite okay as long as it is a 6 degrees of freedom robot. J is a square matrix 6 cross 6. So you can quickly take inverse. Okay. So this is at least true for this. Okay. But is it always possible as you have seen? No. Why? If it is more than 6 degrees of freedom robot, it is not that trivial. So what you have to do, you have to find out Jacobian inverse. Because it is not a square matrix, you cannot do it. So just start with this equation, multiply both sides with Jacobian transpose on the both side of this equation. So what I have obtained is this here, and this is additionally here. So now what is this? This is J transpose J. Now this is a square matrix. It is n cross 6 and 6 cross n. J transpose J will give you n cross n matrix. So this is now invertible. This is as it is. Jacobian transpose is here and the twist vector. Okay. So that is here. Now I can take inverse of this. So now theta dot is J transpose J inverse J transpose twist. So this is known as J plus, commonly known as a pseudo inverse of J. Okay. It is also known as a Muri-Penrose inverse. That is a standard method of finding out inverse for non-square matrix. Okay. So this is what can be used for a robot for which degrees of freedom is more than 6. Okay. If it is less than 6, maybe 5 or 4, a similar technique is there that can be adapted. So these are the way. Even with this, it is not always so much invertible. The matrix can be singular. In that case, this also is not doable. Okay. So what are that? So let us discuss that. So that is known as a singularity. There is another term which is closely related to singularity, that is known as degeneracy. It occurs when a robot loses a degree of freedom and thus cannot perform as desired. Okay. So what is that? What are the conditions when this can happen? So the robot joint reach their physical limits and thus cannot move further. Okay, you have fully extended your robot arm and now you cannot do certain functions. Okay, it is not always true that you see a singular matrix in few of these conditions. Okay, so that is there. So it is robot reaches its workspace boundary. This also is a case, the case which I have just discussed. Physical limits is the joint limit. Okay, your joint cannot go. Let us say this joint cannot straighten up more than this. So this becomes its joint limit and thus it cannot do further action. It cannot move further. So that was your first point. But reaching the boundary space is the extreme joint angle you have already obtained to go to a certain point in the workspace boundary. Okay, so that is the second point. This is where you have maximum reach of the robot is obtained. Okay, this is not the case where kinematically it may be possible, but your joint is not allowing you to go further. So this is the case one. Okay, third one, in the middle of the workspace also, if z-axis of two similar joints becomes collinear. I'll show you by example also. If the z-axis of two similar joints becomes collinear, okay, so whatever you rotate, you see the same action. Let us say if this link goes vertically over this, okay, if it is like this, so what has happened? So if you rotate this or you rotate this, you are going to see the same type of motion. Why? Because you have this axis and this axis becomes collinear. Okay, so this is also a case when it has become a degenerate robot. Number of degrees of freedom of the robot is less than 6. Okay, that is maybe a case with Iskara when it is a 4 degree of freedom robot. You have seen it cannot roll, it cannot pitch, but it can do XYZ translation and it can rotate about the vertical axis. So it can do 4 motions, 2 of them were absent, that is roll and pitch motion of the end effector. So it doesn't have any solution over there. So that is also causing some sort of degeneracy. So we'll talk about this. So the determinant J is 0. This is exactly the case of singularity. The determinant of J is 0. That means it is non-invertible. Okay, that is you cannot obtain joint rate for a given end effector rates. Okay, that is the end effector rate Jacobian inverse theta dot you wanted to obtain. Because this is not invertible, you cannot obtain Jacobian inverse. Okay, so mathematical condition which is responsible for this is known as singularity. The condition that you saw which is not allowing you to take Jacobian inverse, that is what is singularity. So you see practically for point number 2, 3 and 5, 2, 3 and 5, you see they are singularity, whereas degeneracy is all these conditions leads to a degenerate robot. Okay, so effectively only these are when determinant of J is 0. In the middle of the workspace also, if both the axes becomes collinear, it becomes singular also. Okay, and mostly in this case also when it reaches at the extreme of the workspace boundary, your joints may become in a straight line. So I'll show you by example also now. Singularity, which a standard 6 degrees of freedom industrial robot can have. So you see, what is this? Your wrist has come to its extreme position. It cannot go further. So if it was a L-shaped link like this, so this becomes your diagonal, and that diagonal is now coming in line with this. So all the frames now is in a straight line. So you see there is a axis in a dotted line I have shown. You see this, this and this till the rest, all the three are in straight line. So this is known as a elbow singularity. So this is your base joint, this is your shoulder joint, this is your elbow joint. So it is elbow that can oscillate. Okay, that can oscillate, still it can. This will be almost like no motion at all. Okay, so that is a very dangerous situation which can happen. Okay, so this is your elbow singularity. Now what is shoulder singularity? It is exactly the position that I showed you when your last link axis, this axis, is in line with this axis. Let me demonstrate at least one of them. This one you see. What is this? You see, you can move the robot like this. You see, end effector is statically at the same position. The end effector is lying in the same position. Position is same, that is not changing, and the same will be the case if you rotate the last axis. The last axis and the base axis both are in the single line. So if you look from the top, you see it is not causing any displacement. This is the last axis motion, and same will be the case when it rotates from the base. Okay, so this is a typical case of shoulder singularity, wrist singularity. What is this? In this case, you have axis 4 is in line with the last axis. Got it? Two of them are in a single line. Okay. So what is this? It is the frame which is here, that is like this, which is able to rotate it like this, whole of the wrist. Now you have last axis also can make the same movement, and both are in single line. Okay. So this is known as a wrist singularity. I can show you even with this robot. So you see this axis, the axis over here and axis over here, both are in line. So you can move like this. Okay, that is there, and you can move like this. Both are in a single line. Okay, so moving any of these will give you same sort of motion. So this also is a singularity which is known as a wrist singularity. So these are some of the singularities that industrial robot normally sees. Okay, other than these, you already know if it reaches its boundary like this, something like this, so it can go, quite probable that it is also singular. Okay. Okay. So now let us analyze 2R planar arm once again for singularity. So you know this is your Jacobian. This is your Jacobian. You have just now derived for this. So in order to make it singular, the determinant of this should become equal to 0. So equating JV determinant to 0, I get this. You simply take determinant of this. Okay, this into this into this, taking subtraction in between. So that can be equated to 0. Solving it further, I got till here. This is trigonometrical equations. You can simply reduce it further and you can obtain sine theta 2 is equal to 0. You remember S1 is sine theta 1, C1 is cosine theta 1, S12 is sine theta 1 plus theta 2, and likewise. So you see sine theta 2 equal to 0. So this gives you a solution like this, theta 2 equal to 0 or theta 2 equal to 180 degree. In both these positions, this angle becomes equal to 0. That means it is in a straight line. It has reached here. So it is a type of boundary singularity it has obtained. Okay. Or you may call it the elbow is in a straight line to the base and the end. So it is a elbow singularity also when it cannot go further. Okay. So this is a position when it is singularity. In case of theta 2 becoming 180 degree, this is totally inward folded. So this has come down till here and your link has come here. There your end effector comes here. Okay. So in this case also you have end effector, elbow and the base joint, all the three are in a straight line. Okay. And then again you lose your degrees of freedom and you become singular. Okay. So this is also a case. So this is the physical significance of that. This saw you can analyze for singularity of any given robot like this. So iterative inverse kinematic solution, that is also known as a resolved motion rate technique. Why is that used? You already know this expression, that is twist equal to Jacobian into theta dot. Okay, this is very well known equation now for you because it relates the joint rates to the end effector rates. So provided you are given end effector rates, can you know the joint rate? So you know you can take inverse. Okay, so that can be written as delta theta is equal to Jacobian inverse delta of twist. To understand it better, let us just say it is having some delta x, delta y and delta z. Maybe these angular things becomes equal to 0. So I am not talking about that for simplicity. So this is your end effector velocity. Okay, so that comes here. Velocity, because it is just a rate and with same time variable, both are taking differentiated. So the relation holds true still. So it is this. Okay. This can be, the robot can be made to move using this, using small increments. So this equation, you know, is true for very, very infinitesimally small steps. If you can move, you can do delta theta. Let us say your robot is already in certain position. Okay, so this is the place you can calculate your theta 1, theta 2 and theta 3. You can calculate your Jacobian. You can take Jacobian inverse also for this. So if at all you want to have, this is a variable, this is not a constant. It changes for each and every location of the robot. For every pose it changes. Okay, so this is a variable with theta angle somewhere in between. It's a non-linear relationship, so that is there. So this is your end effector. So this is your end effector rate. So if you want to make it move with small incremental displacements like this, and every small amount of time, so you can calculate what could be the small amount of increment in theta 1, delta theta 2 and delta theta 3. So you can go to that new position, that is, if it is at x, new position. So you know now, if you change by delta thetas in all the joints, you can take it to a new position. So this is what we want. So without actually doing inverse kinematics and get to the new joint angles, okay, you are able to calculate your new joint angles using this. So you are able to displace your robot by certain distance, small distance, and you can make it move by incrementally changing your joint angle. Mind it, this is true only for very small displacement. So this is your new equation. So that is theta time of k plus 1, that is the next point, is first point plus j inverse of this. This is delta theta. So this is the delta theta that you are trying to add on to the previous joint angle, getting to the new joint angle for change in position. Okay. So can be further written as, so this is your change in position of the end effector. This is where you want to go. This is where you were. Okay. So taking the difference, multiplying with Jacobian inverse gives you delta theta vector, and that is added to this initial joint angle, get to the new joint angle. So this is how. So you can move this way also. Okay. So this is your time step. This is your pose of the end effector. Mind it, it is pose. It is not just change in position. It is change in orientation as well. Okay. So that is with time. So I can show you this using virtual robot simulator that I was just using. Okay. I can make it like this. Let us first try moving in Cartesian with this only. Let us see if it moves. So if I want to move it along x by certain distance, 20 I have fed here. So if I start it, you see it has just gone wrong. Okay. It says some error has popped up and finally it is unable to move. Okay. So it cannot move from a singular position. So that is, limit is always there because this type of technique uses Jacobian inverse and this is unable to move. Okay, let me just displace it by certain angle. So I will not make it singular now. Okay, let me take it to some other position. So can I move it now? You see it is not a singular one. Now I'll try to move by same distance and see it is able to move. Let me give some little more displacement. Okay. So now you will see. So this is moving, you see. So I have given along Y, I have moved by 50. Let me move also along Z by, let's say, 70. Okay. So this is using number of steps I have taken 100. Okay. So this is able to move, you see. So it is moving along X, along Y, along Z. So it is able to perform. So this sort of motion can be achieved using small incremental steps. For such a small distance like 70 mm, I have divided by something around 100 steps. So it is very, very small displacement it is doing, and that is why it is able to do it. It can reach where I have commanded it to go. So this type of method works at least for a small incremental distance and slow velocities. You can very well attain this. Okay. So yes, coming back to my normal slide. So this is it. But the drawback you already know, the system converges only to the nearest solution. Let us say you wanted to go to inverse kinematic solution out of the 8 different solutions. It won't take you there. It will take you to the nearest one. So that is sometimes beneficial also. And it is only valid for non-singular Jacobian. You cannot pass through a place which is singular. Okay. So let us do acceleration analysis also. So we already know twist is Jacobian times of theta dot. So this is a common equation that we have started quite number of times today. So this is it. So if you want to obtain acceleration, we'll be using this. So this is your velocity matrix. Okay. Derivative dot, you can write, so it is j theta dot, so it becomes j theta double dot plus j dot theta dot. It is just differentiation, nothing else. So same way, the way you differentiate two variables, same way you can differentiate even vectors or even matrix. So j is a matrix, theta is a column, it is called as a vector here, angular and linear accelerations. So this is what you wanted to obtain. And what all things you needed here is j dot. Okay. So what is theta double dot? It is nothing but joint acceleration. So in order to obtain end effector acceleration, you need to know the joint acceleration also. Let us say you are holding something at your end effector, and if at all it is moving with an acceleration, I want to be very sure if that with that acceleration, whatever are the pseudo forces which are generated due to inertia, okay, it should not come out of the gripper. So that is why sometimes acceleration analysis is also very, very important. Okay. So this is it. And then j dot can be calculated like this, taking derivative of ei cross aie. That is what you did. So this was your general any ith term of your J matrix. Okay. So you just take the derivative of this as well as this. So taking derivative of this can be expanded like this. Okay. So now you know J dot, theta double dot is already known. Okay. So these terms are known. So now you can obtain the end effector, angular and linear accelerations. Okay. Now you can use this expression again on 2 degree of freedom arm, and you can calculate twist rates. Okay. That is linear and angular accelerations. Okay. That's all. Thanks a lot. So with this we'll end today and this module also. Okay. And the next module is very, very new for you all. So that is industrial robot installation and commissioning. That is when you buy a new robot, what all things that you do. That's all. Thanks a lot.